Hello, hello, hello. Think we should be live. Uh, let's double check that. Um, wait, what am I doing? I don't know why I'm so lost right now. Okay, yeah. I'm looking for. Oh, are we live? Okay, yes, we are. All right. At least according to YouTube. I don't know why. All right, it's going. All right, so we are following up on yesterday's stream for the Lingua Franca handbook. Last thing we went over yesterday was super dense time. I'm not gonna lie, I don't think I fully grok um, the details of it all. Um, like right now, even though I just read through this right now, I don't think that I could fully give a correct explanation of the super dense model of time. I know that, as it says right now on the screen. Excuse me. Oh, wait. Is my screen frozen? No, it's going. Okay. Um yeah, I mean, I get that there is, there's physical time, there's logical time, there is the concept of a tag. I get that. Um, what is this? So I get that part. Um, I get that there is such a thing as a micro step, and I think my understanding is that a micro step is actually some sort of slice uh, between, or it represents a slice of time, or I guess logical time. Um, I was gonna say a slice of time between two logical times. See, uh, not great. Um, yes, so I'm not really sure what the difference is between logical time and micro step, except for the fact that a micro step is what advances the logical time. So by that theory, we should be able to determine. Um, or maybe it's the amount of execution steps between any two logical time steps. So it maybe going from one logical time to the other will be considered, let's say, a micro step and a macro step, and then between them you then have the concept of micro step. Uh, that's about how much I think I understood. And I think just by looking at this, I think that's exactly what it is. Um, the logical time. Um, time since thought 0. So yeah, the elapsed logical time hasn't changed, but then you have the micro steps that changes. So the reported elapsed logical time has not advanced in the second reaction, but the fact that X is not present in the second reaction proves that the first reaction and the second are not logically simultaneous. The second occurs one microstep later. So yeah, I think the concept of microstep, I think it really boils down to being able to have a logical, some sort of logical ordering of the reaction executions within the runtime. Well, okay, I don't know if it's within the entire runtime or just the reactor itself. But my guess is it's probably across the runtime, meaning the main reactor, which hosts all the other reactors. Anyway, but we'll just go ahead and just go to the next concept, model reactors. And yeah. Alright, this article has examples in the following target languages. The basic idea of model reactors is to partition a reactor into disjoint subsets of reactions or other components that are associated with mutually exclusive modes. In a model reactor, only a single mode can be active at a particular logical time instant, meaning that activity in other modes is automatically suspended. Transitioning between modes switches the reactor's behavior and provides control over continuing or resetting the previous history of the entered mode. Okay. So modes are mutually exclusive. And when you transition between any two modes, you're basically resetting the state to an initial state for the target or the mode that you're transitioning to. And I mean, really, it goes without saying, mode here can be substituted for the word context. Basically, your reactor is changing context. Yeah. Excuse me. Modes can be defined in any reactor except federated ones. Each mode requires a unique per reactor name. Okay, so per reactor has to be, and can declare contents that are local to this mode. There must be exactly one mode marked as initial. Okay, so if you're gonna opt into the mode to the mode model, if you're gonna switch it to the mode model, then there must be at least one. That's initial. So I mean, this sounds like by default every reactor always has one default mode, and that's the initial one. It's just that you don't have to specify that when you are in fact only using one mode. But if you're gonna use multiple modes, then that's when it becomes required to specify that initial mode. A mode can contain local state variables, timers, actions, reactions, reactor instantiations, and connections. While modes cannot be nested in modes directly, hierarchical composition is possible through the instantiation of modal reactors. The main exception is allowed contents in modes of port declarations. Wait, what? The main exception in allowed contents in modes of port declaration, as they are only possible on reactor level. Okay, so the input and output port always have to be at the reactor level. Excuse me. Yet, modes share the scope with the reactor and hence can access ports, state variables, and parameters of the reactor. Only the contents of other modes are excluded. So, okay, so a mode can have its own variables. It can have its own ports, but it can have its own state variables, but not its own ports. That makes sense to me. Oh, and can have its own reactions and reactor instantiations. Interesting. So, yeah, it really is a full scope context. Well, scope/context within a reactor. Probably simplifies the development of, really complex reactors. Because without something like this, that you probably end up having to create, external reactors that you then use to compose inside a bigger reactor. And I mean, that's fine probably for most things, but maybe in some cases you just want to really encapsulate, like in some cases, locality of logic is highly what's the word I'm looking for? I guess it's just better, right? It just makes life easier when it comes time to what's happening on my screen? When it comes time to do some debugging and all that. Yeah. Okay. Reactor. Okay, a model reactor can still have reactions, reactor instantiations, etc., that are not located in modes. It will consequently be executed independently. Gosh, words. Independently from mode activity. Mode transitions are declared within reactions. If a reactor has modes, if a reactor has modes, reactions inside modes are allowed to list them as effects. Such an effect enables the use of the target language API to set the next mode. Okay. So normally, this will be an output port, usually, if there is a side effect on a reaction, but you can also specify a mode as a target or as a side effect, which basically symbolizes a transition from one mode to another. You can also specify the type of the transition by adding the modifier. You can also specify the type of the transition by adding the modifier reset mode. So in this case, it will be reset 2 or history 2 in the effect of the reaction signature after the arrow. For example, a history transition to the state 2 is enabled by listing history 2 among the effects of the reaction. The reset variant is implicitly assumed when the mode is listed without modifier. But what does history mean, though? Are we gonna go through that? I guess reset means you're resetting the state of the mode. And history is you just pick up from where you left off within the mode. Or maybe it's not even just within the mode, it's the whole reactor that you're resetting if you do this. And if you do this, you just keep on, you keep the existing state and just keep moving forward with it. That's my guess. Execution semantics. The basic effect of modes is that only parts that are contained in the currently active mode or outside any mode are executed at any point in time. The basic effect of modes is that only parts that are contained in the currently active mode or outside any mode. Okay, so in the modal state, I guess the modal model. Oh no, the modal model of computation here. In that model, all the code that execute will either be inside the active mode or everything that's not in any other mode but at the quote-unquote global reactor, or I guess local reactor scope. This also holds for ports that are nested in multiple ancestor modes due to hierarchy. Consequently, all those ancestors must be active in order to execute. Reactions in inactive modes are simply not executed, while all components that model timing behavior, namely timers, schedule actions, and delay connection, are subject to a concept of local time. That means while a mode is inactive, the progress of time is suspended locally. Okay, so yeah, but okay, in that specific mode. How the timing components behave when a mode becomes active depends on the transition type. A mode can be reset upon re-entry or upon entry, returning it to its initial state. Alternatively, it may be entered preserving its history. Yeah, basically what I guessed here. Okay, wait. How the timing components behave when a mode becomes active depends on the transition type. A mode can be reset upon entry, returning it to its initial state. Alternatively, it may be entered preserving its history, which only has an actual effect if the mode was active before. In the latter case, all timing components will continue their delays or period as if no time had passed. During inactivity of the mode, as if no time had passed during inactivity of the mode. The following section will provide a more detailed explanation of this effect. Okay. Upon reactor startup, the initial mode of each model reactor is active. Others are inactive. Okay, makes sense. If attack TM, all reaction of this reactor and all its contents have finished executing, and a new mode was set in react. If attempted, all reactions of this reactor and all its contents have finished executing, and a new mode was set in a reaction, the current mode will be deactivated, and the new one will be activated for future execution. This means no reaction of the newly active mode will execute at type TM. The earliest possible reaction in a new mode occurs 1 microstep later at Tm plus 1. Hence, if the newly active mode has, for example, a timer that will elapse with an offset of 0, okay, let's start this over again. Hence, if the newly active mode has, for example, a timer that will elapse with an offset of 0, it will trigger a Tm plus 1. In case the mode itself does not require an immediate execution in the next microstep, it depends on future events, just as in the normal behavior of LF. Hence, modes in the same reactor are always mutually exclusive with respect to superdense time. Superdense time, I think I'm gonna need to reacquaint myself with that. at some point. A transition is triggered if a new mode is set in a reaction body. As with setting output ports in reaction, a new mode can be set multiple times in the same or different reactions. In the end, the fixed ordering of reactions determine the last effective value that will be used. The new mode does not have to be a different one. Oh, interesting. The new mode doesn't have to be a different one, which means that technically you can just, it's like you just want to reset the state in a mode, or maybe do a self transition that slightly affects the current state. Well, maybe slightly is not the right word, but anyway. It is possible for a mode to reset itself via a reset transition. Excuse me. In case a mode is entered with a reset behavior, all contained modal reactors are reset to their initial mode recursively. So by contain, I think just to make sure I understand, they mean, because we did read earlier on the page that a mode can instantiate well, it has its own reactions, but it can also instantiate its own component reactors. So when you reset it, it's also recursively resetting all its children modal reactors. All contain state variables that are marked for automatic resets or reset to their initial value. Any contained reactions triggered by reset are executed, and all events, actions, timers, delayed connections that were previously scheduled from within this mode are discarded. Reading all this just makes me think of real-time systems. It's like, hey, the timer went off. It is what it is. Like, if you're not done or whatever you were doing before, that's over with. Like, things need to happen at a particular time, and there's no ifs or buts. Anyway, note that contain refers. What does it mean by contain? Oh, contained. Okay. Gosh, it's so slow. Note that contained refers to all contents defined locally in the mode and in the local reactor instances recursively that are not otherwise enclosed in modes of lower level. Excuse me. Whenever a mode is entered with a reset transition, the subsequent timing behavior is as if the mode was never executed before. If there are state variables that need to be reset or reinitialized, then this can be done in a reaction triggered by reset, or by marking the state variables for automatic reset. State variables are not reset automatically to the initial conditions. Wait. Oh, okay. Alright, I guess I just read this. So you either do it via the reactions, via the reset trigger, or you have automatic reset. Okay. State variables are not reset automatically to their initial conditions because it is idiomatic for reactors to allocate resources or initialize subsystems, allocate memory or sockets, register, and interrupt or start a server. In reactions triggered by the startup, in reactions triggered by the startup, and to store references to these resources and state variables. If these were to be automatically reset, those references will be lost. On the other hand, if a mode has been active prior and is then re-entered via a history transition, no reset is performed. Events originating from timers, scheduled actions, and delayed connections are adjusted to reflect a remaining delay equal to the remaining delay recorded at the instant the mode was previously deactivated. As a consequence, a mode has a notion of local time that elapses only when the mode is active. So it's almost like you're just freezing time. I wonder if just crossed my mind that could you build a time travel debugger with Lingua Franca? Maybe. Probably. Okay. Local time. From the perspective of timers and actions, time is suspended when a mode is inactive. This also applies to indirectly nested reactors within modes and connections with logical delays if their source lies within a mode. The above Lingua Franca model illustrates the different characteristics of local time affecting timers and actions in the presence of two transition types. Oh, okay, it's talking about this all the way up there. Okay, let's start again. From the perspective of timers and actions, time is suspended when a mode is inactive. This also applies to indirectly nested reactors within modes and connections with logical delays if the source lies within a mode. Okay, if the source lies within a mode. Okay. So this is the consequence of the time freeze effect. Alright. The above Lingua Franca model illustrates the different characteristics of local time affecting timers and actions in the presence of two transition types. It consists of two modes, one the initial mode and two both in the modal reactor. The next input toggles between these modes and is controlled by a reaction at the top level that is triggered by the timer T. Let me see. Okay. What are they talking about? Okay, it's not clear which one exactly. At least there's no mention, in the actual code example, I don't see some of the stuff that they're referring to here. Okay. The next input toggles between these modes and is controlled by a reaction at the top level that is triggered by the timer T. Oh wait, is that this here? Yeah, I think it might be this. Okay. After 1 second, a mode switch is triggered periodically with a period 1 second. Each mode has a timer T1, T2 that triggers a reaction after an initial offset of 100 milliseconds and then periodically after 750 milliseconds. This reaction then schedules a logical action with a delay of 500 milliseconds. This action triggers the second reaction, which writes to the output. It's kind of hard to follow this concretely without the actual example to see. That's kind of annoying. This action triggers the second reaction, which writes to the output port out. The main difference between the modes is that one is entered via history transition, continuing its behavior, while 2 is reset. History behavior is indicated by an H on the transition edge because it enters into the entire history of the mode. Yeah, it's hard to follow this because there's no example here. This whole area here says the above illustrates the relation between global time and, but there's no above. Yeah, there's nothing here. This page definitely needs some work. Model reactors. I'll make note of that. Start up and shut down. A challenge for model execution is the handling of startup and shutdown behavior. These are commonly used for managing memory for state variables and handling connections to sensors or actuators or starting joining external threads. If reactions to these triggers are located inside modes, they are subject to a special execution regime. First, startup reactions are invoked at most once at the first activation of a mode. Second, shutdown reactions are executed when the reactor shuts down, irrespective of mode activity, but only mode activity. But only if the enclosing modes have been activated at least once. What? Excuse me. Second, shutdown reactions are executed when the reactor shuts down, irrespective of mode activity. Okay. So regardless of what's going on within the current mode, it just shuts down. But only if the enclosing modes have been activated at least once. Okay. And what if they have? So every startup has a corresponding shutdown. Third, as mentioned before, the new reset trigger for reactions can be used if a startup behavior should be re-executed if a mode is entered with a reset transition. Shutdown reactions are executed when a reactor shuts down, irrespective of mode activity, but only if the enclosing modes have been activated at least once. Yeah, but what if they have though? Then it has to wait for all the enclosing modes to to shut down, or to, I guess, suspend. Third, as mentioned before, the new reset trigger for reactions can be used if a startup behavior should be re-executed if a mode is entered with a reset transition. Note that this may have unexpected implications. Startup behavior inside modes may occur during execution and not only at program start. If you have the reset stuff on those on reactions of those modes, I think multiple shutdown reactions may be executed, bypassing mutual exclusions of modes. Oh, okay. So for shutdowns, that's the only time that every single mode concurrently. Is it concurrent in that case? I guess in parallel. I mean, I guess it's the only time when they're not mutually exclusive. Reactors that are designed without considerations of modes and use only startup to trigger an execution chain may not work in modes and cease to function if we entered with a reset. This chapter is pretty dense. That's 2 chapters in a row now. Super dense time and model reactors. But I feel like I have a better handle on model reactors than model reactors than what was the other one? Super dense time. Let's see. Is there anything? No, there's no. Request response. I was looking for an example with an example with what is it that I'm trying to say? An example with modes. I guess I could do a search mode something. Oh man. This is new. This annotation here. I haven't come across this before on the side thing. Election. Is the main reactor. It says federated. Yeah. Okay, so yeah, so there are different modes. But I wonder what, yeah, I'm not sure what this is for. Let me see. Okay, Lingua Franca program represents a distributed leader election system with 3 nodes. Each node has an associated unique ID. And the goal is to elect the node with the highest ID as a leader. The program consists of a federated reactor that connects 3 nodes, 3 node reactors in a ring topology. Each node initially broadcasts its ID, and upon receiving an incoming ID, it compares it with its own. If the received ID is greater than its own, the node forwards the received ID after a 10-millisecond delay. If the received ID is equal to the node's own ID, it declares itself as the elected leader and transitions to the elected mode. The leader election process continues until the node with the highest ID is elected. Junior, it's 2 years ago. Oh, wow. 30 commits. Oof. Let's see. Is there like a timeline thing? I guess they've added annotations to the runtime. Distributed time. Oh, I think these are all for, well, not all of them, but most of these changes are for the distributed time example. Oh. Distributed time. Let's see. Oh wow, they have a lot more examples in C than other languages, which is fine. This example demonstrates, well, it's just like I'm just realizing that, well, I guess not just now, but in general. I mean, if this language, I guess you can call it meta language, is handled well, it could really be a staple for distributed, well, for deterministic simulation testing. Like, I mean, I guess it depends on also how the actual runtime is being implemented. But I think one of the reasons why it stuck with me, even from the first moment that I became aware of it, was the fact that their stated goal is that they want a deterministic runtime. Now, obviously, you add multi-threaded, distributed code, and all that. It makes it even more interesting. And, getting rid of concurrency bugs is like one of the key selling points of the deterministic simulation testing. So they call it a coordination language. I wonder how many of those there are. React oriented. Like, are there like a true pioneer? Well, I don't want to say true pioneers. Like, as if they are fake pioneers. Well, yes, there is such a thing as fake fake pioneers. Uh, but I guess my point is, I have no doubt that the work that they're doing is, you know, as far as I know, which may not be saying much, I don't know that there are many other projects out there who are doing the work that they're doing. And the thing is, this is not new. Like, this is a multi-year, multi-institutions, multi-institutions project that has been going on for a while. Um, so it's not just like you know, just a new thing. And I think the leader of it all, Edward Lee, I believe his name is. I think he's been working on this for years and years and years. So I have no doubt that this is meant to stick around for a while. Like, it's not just something that's just going to disappear. I love how I somehow ended up on a research paper from here. I think we were supposed to go straight to deadlines. What time is it? Okay. Let me see. So let's read the abstract of this, then go back. Because the title was just interesting to me. Distributed reinforcement learning. Let me see if I can make this bigger. Okay. Distributed reinforcement learning frameworks are essential for mapping reinforcement learning workloads to multiple computational resources, allowing for faster generation of samples, estimation of values, and policy improvement. These computational paradigms require a seamless integration of training, serving, and simulation workloads. Yep, simulation workloads. Deterministic simulation testing, what I was alluding to earlier. The fact that it seems like such a right programming model for building simulations. Now, I don't know in terms of, actual performance characteristics if it can keep up with, the current frameworks that people use for simulation testing. But I think it probably does at least okay. And, then you add the whole deterministic goal that is meant to be built into the runtime. Or the fact that it's a coordination language, and I think I can totally see how it's a language that would be really useful for building simulations. Okay, existing frameworks such as Ray 22 are not managing this orchestration efficiently, especially in reinforcement learning tasks that demand intensive input-output and synchronization between actors. As such, we have optimized Lingua Franca, a polyglot coordination language for synchronized parallel reinforcement learning workloads. The development of our proposed framework, Lingua Franca for reinforcement learning, represents several significant contributions to the field. So it's a distributed framework that integrates the critical components of all RL tasks, training, simulation, and serving into a single cohesive system. LFRL is built on top of the reactor model and supports true parallelism in Python, thereby significantly decreasing synchronization and I/O overhead. LFRL also supports seamless distribution of computation to GPUs when that computation can benefit from it, further accelerating deep RL workloads. On average, LFRL outperforms Ray in generating samples from OpenAI Gym and Atari environments by 1.21 and 11.62 by a factor of. I should have prefixed that for the numbers. Reduce the average training time of synchronized parallel queue learning by 31% and accelerated multi-agent RL inference by 5.12x. It represents a leap forward in the field of distributed RL, particularly in better satisfying the particular needs of deep reinforcement learning workloads. Its unique design principles and innovative features position it as a critical tool for researchers and practitioners in the rapidly evolving landscape of RL. All right. How did I end up here again? Oh yeah, I think I was I was co-design of modern cyber physical system often make use of heterogeneous systems on chip with configurable logic or provide adequate computing power and flexible I/O. However, modeling, verifying, and implementing the computations spanning CPUs and with configurable logic are still challenging. The hardware and software components are often designed by different teams and at different levels of abstraction, making it hard to reason about the resulting computation. We propose to lift both hardware and software design to the same level of abstraction by using Lingua Franca coordination language. Lingua Franca is based on a sparse synchronous model that allows modeling concurrency and timing while keeping a sequential model for the actual computation. We define hardware reactors as a subset of the reactor model of computation underlying Lingua Franca. We also present and evaluate reactor chisel, a hardware runtime implementing the semantics of Okay. We also present and evaluate reactor chisel, a hardware runtime implementing the semantics of hardware reactors and an extension to the Lingua Franca compiler, enabling reactor-oriented hardware software design. That sounds hardcore. What does MOC stand for? I keep saying MOC. A model of computation. Okay. And what is SOC? this occurs system on chip field. Integrate multiple. Wait, so FPGAs. Refresh my memory. What are FPGAs again? I know it has something to do with you basically programming your logic straight up onto the hardware. But is the programming of the hardware, is that of the, I mean, okay, let me just read. Okay. So yeah, so you don't program, so it's not a way to program onto CPUs or GPUs. They're all their own thing. I mean, if you think about it, if it wasn't for the cost of development, I mean, this is a completely ridiculous scenario, but in a world of AGI or ASI, whatever, why would you, and you're a hyperscaler, why would you, I mean, doesn't NVIDIA kind of lose its edge? Like, why wouldn't a company like Apple, who has so much money, so much cash on hand, now just build a system where they have their own data centers that are mostly all just FPGAs? Because, the AGI or ASI can just configure the custom logic onto the hardware like that. An FPGA is a chip that lets you implement a digital circuit inside it. Anyway, I think the gist of it is you want maximum control for maximum speed or maximum performance, to be more general. Anyway, this actually sounds like a pretty interesting research paper. Maybe we'll read that as a follow-up to finishing the manual. Could be interesting. FiberFlex, real-time FPGA, fiber sensor. Wireless communication. Rabbit holes everywhere. Stream processing, which involves real-time computational data as it's created and received, is vital for various applications, specifically wireless communication. The evolving protocols, the requirement for high throughput, and the challenges of handling diverse processing patterns make it demanding. Traditional platforms, grapple with meeting real-time throughput and latency requirements due to the large data volume, sequential and indeterministic data arrival, and variable date rates, leading to inefficiencies in memory access and parallel processing. We present Canalys, a throughput optimized framework designed to address these challenges, ensuring high performance while achieving low energy consumption. Canalys is a hardware-software co-design system. It includes a programmable spatial architecture, flux stream processing unit, proposed by this work to enhance the data throughput and energy efficiency. Flux SPU is accompanied by a software stack that eases the programming process. We evaluate Canalys with 8 distinct benchmarks when compared to CPU and GPU in mobile SoCs. Gosh, what was SoCs again? Shit, I just read that somewhere now. To demonstrate the effectiveness of domain specialization, Canalys achieves a average speed up of Jesus. That's nothing to sniff at. And energy savings of, assuming that these numbers are true, that's money right there. That's that's not a joke for profit margins. In contrast to equivalent ASICs of the benchmarks, the average energy overhead of Canalys is within 2.4%, successfully maintaining generalization without incurring significant overhead. How much data are we talking in terms of movement? Wait, so they are proposing as wait, is Flux SPU something that already exists, or they are making that up as part of this research? Excuse me. Our goal is to design a throughput optimized framework 2.0 architecture with co-design software stack. The goal is to achieve the performance and efficiency of the application-specific integrated circuits implementation, yet retain the flexibility of programmable systems. Our framework, Canalys, is specifically designed, optimized to improve the throughput of real-time stream processing of wireless communication workloads that have little or no control flow. As shown, provide examples and benchmarking. A domain-specific instruction set architecture. Flux stream processing unit. This ISA co-design with microarchitectural optimizations specifically enhances the proposed architecture's ability to loop structures and reduces the initiation interval. Third, we connect the nodes to form a flux SPO fabric, a multiple instruction, multiple data. This is coming, by the way. I don't know. Multiple instruction, multiple. I think right now we have SIMD. I think we also have single program, multiple data, SPMD. This is the first time I'm reading of multiple instruction, multiple data. But it's like Thanos. You can't run from it. Destiny will arrive. All the same, we are gonna make our way to this because it's necessary. Like Cooper says in Interstellar, when the thing is spinning, he needs to match the rotation in order to dock. And I think the co-pilot, the assistant Mars, tell him it's impossible or something. He's like, it's necessary. I was like, let's go. It was so epic. I don't know, can I show it? Is YouTube gonna give me a hard time about showing this? Oh, hands on audio. Wanna see that later. Generate docs from code. That should be interesting. Kubernetes, a new Skynet. It's building 100 billion company. What exactly are they? What you say building? I came here for a reason. What was it? Interstellar. It is necessary. Is it this? Yeah.
And then we can talk about completing the mission.
Dr. Mann, listen to me.
This is not about my life or Cooper's life. This is about all mankind. There is a moment.
Gosh, this was
It is not.
yeah, and it's the fact that it just goes quiet when the explosion hits. That's crazy. Gosh, this was epic, man. Well, it is fucking epic.
Cooper, there's no point using our fuel to chase...
Analyze the Endurance's spin.
Now, you say this is where AI and co-pilots will be really useful, right? It's like he's a pilot. He's a domain expert in what he does. But, you know, having an AI be able to answer that question within this context is so valuable, right? And I'm sure that in this fictional reality or whatever, the AI is not just hallucinating a response, right? It's like, analyze this for me. Gosh, I can only imagine the amount of data that needs to be processed. And it's, I mean, so you can imagine it's a matter of ingesting data from sensors and having, gosh, it would be crazy if part of its algorithm is the, well, it probably is the case, that part of its algorithm is being able to assemble simulations from, you know, whatever components or primitives that it has as part of its core programming, being able to assemble simulations just in time or slash in real time, and yeah, basically have ingest data based on whatever directives it's been given, assemble a simulation and run it, probably run multiple simulations, assess the reliability of the outcome of the simulations, and then provide a response. And it has to do that within a very tight time budget. Especially, I mean, imagine this context. I mean, not only do you need that answer to be correct, maybe not perfectly correct, but like the level of certainty should be probably, like, you know how you have AWS gives you how many nines availability, nines, how many does, yeah, 11 nines. Thor's the co-pilot in that scene. I wonder what its what is the threshold of its decision making. Like, it runs a simulation, probably several iterations, and it probably also needs to decide on how many iterations will constitute a statistically significant sample. And then you have to wonder what is the threshold in terms of it being able to answer the question confidently and say, you know, XYZ with a confidence level of how many nines? I don't know, 100 nines? I mean, 100 nines would be, it's probably closer to 100 nines, right? In this scenario here. I mean, this is life or death, right? And considering everything, you better have as many nines as possible. If 100% is impossible to get to, like, in terms of confidence level. Anyway, all of that is to say, these AI models are gonna get better, and I think the best thing you can do is probably build some sort of expertise in a particular domain and really know how to leverage their capabilities. I mean, if you just take the context of this scene, of this movie, I don't think Cooper would be considered an AI engineer by any means. Like that's not, he's a pilot and he, that's what he does. But what we are being sold, and you definitely buy it, is that he's a competent pilot and he knows how to use the tool, right? And in that moment, he knows the tool well enough to know that this is an answer that can be trusted. But then that means that somebody had to build, by somebody I mean there had to be efforts to build this AI tools. Jesus, 9 years ago? Gosh, when did Interstellar come out? It's already been that long. Jeez. Anyway, yeah, somebody, the people who built the AI assistant must have, like, yeah, it's amazing. Like, to think about what we have right now, the Gemini Pro, the Claudes, the GPT-4 and all that. Now compare that to what this particular AI Copilot is doing here. Like, I don't think we have any machine right now on Earth, to the best of my knowledge. I could be wrong, but I don't think that we have a machine, even by, I get it, this is a fictional world, and they're talking about, this is not even going to Mars. This is, they've been on a planet through a black hole, right? That's what happens. They travel through a black hole, and there's time dilations and all that. So very fictional world. But still, let's just put things into perspective here. Yeah, like, we're way off from such a machine to be in this particular context, being able to process the amount of data that this thing is processing, to be able to provide a response that is as close to deterministic as possible given the context. We are so way off from that. So, yeah. Anyway.
What are you doing?
Docking.
Endurance rotation is 67, 68 RPM.
Okay, get ready to match our span with the retro.
And again, I think there's no reason to believe that. Again, based on the scenario here, the understanding is that the machine, the AI, is doing this in real time, right? It's not something that's pre-computed or something. No, it needs to process this data in real time. And I'm sure that, just in terms of throughput, the amount of data that it's processing right now probably dwarfs the amount of data that entire enterprises are processing in a whole year. Like, it's probably processing the equivalent of whatever Netflix processes in an entire week or something. And it's doing that in a matter of seconds. At least that's my feel for what's happening here.
Retro thrusters.
It's not possible.
No, it's necessary.
Let's go. I don't know, man. If you watch this movie and you get to this part and you don't just get the chills, I don't know, man. This is it. This is why we make movies. For moments like this, it's like, gets you. I don't know. I was hyped. Even now, just watching it, I'm hyped.
Match our span with the retro thrusters.
It's not possible.
Like, there's something about just being not only competent, but being in the thick of it, and just knowing that, like, there's no other option. You just gotta do it.
No, it's necessary.
Shit.
Endurance is hitting stratosphere.
She's got no heat shield.
Hey, she ready?
Ready.
Again, just, yeah. I'm just still trying to wrap my head around the fact that, I guess I never really sat down to think about it. But just, I mean, obviously it's 9 years ago, but being the age that we are right now with AI and everything, and how it's so easy to get frustrated by them in terms of the fact that we are nowhere near being able to get deterministic answers, even for simple things, right, that you would expect a powerful AI machine to be able to just get. And yet here we are with this machine, and it's doing that, but it's doing that in real time with the ridiculous amount of data that it's processing.
Cooper, this is no time for caution.
Hey, if I black out, you take a stick.
Guards,
Yes, and again, the fact that you have a machine to which, in this context, you can tell it, hey, if I black out, you take over. We are nowhere near building such a machine right now. Again, to the best of my understanding, I mean, we're still trying to figure out full what are they called? Autopilot on cars, whatever. We're still trying to figure that out. Right? Now, is there an argument to say that driving in a busy city is a... No, I didn't say Siri. Shut up. That driving in a busy city, like, I don't know, New York, downtown, on Manhattan, downtown, whatever, I'm not very familiar with all the New York scene. Anyway, yeah, just driving there. Could you argue that that's a more challenging task than what is happening here? I don't think so. Like, just the sheer amount. I mean, I'm sure there's a lot of data that needs to be processed for self-driving cars, full self-driving cars, like in real time, but I don't think it's anyway close to what TORS is doing here. Like, you know, and yeah, like, and the fact that in this context, the pilot is basically saying, like, there's enough trust built into the machine that the pilot can say, hey, if I black out, you take over. Like, that's, you wouldn't say that to GPT-4 right now, or 4.5, or Gemini Pro, or whatever. Like, yeah, shit, I wouldn't let any one of them near my bank account. So, yeah, all of that again is to say that there's such a long way to go in terms of what we can do with artificial intelligence.
Ready to engage the docking mechanism.
Endurance is starting to heat.
20 feet out.
I need 3 degrees starboard, Cooper.
10 feet out.
Cooper, we are lined up.
Initiating.
Again, that's not a decision that a robot can just hallucinate. Like, it has to be freaking correct to the, I don't even know what measurement we're talking about here. And that makes me chuckle, because we've had a space launch go bad because scientists didn't figure out that they were using different units of measurement. And yet here we are with a scene where you have an AI co-pilot that is the one saying, yeah, we're good, like everything is in alignment, and the amount of precision that it has to get right here is non-trivial. Gosh, and also just the music. Christopher Nolan. You son of a bee. No horror, no monsters, no evil aliens, no bloody violence. Greatest piece of science fiction movie. Oh, so that's what that was. I just thought it was because of overall just more hours training and more resistance. But I think it's not just that. I think it's also, based on this, it sounds like it's also a matter of technique. So you tilt in your head, like that level of detail. There are not many directors who can handle that.
Come on, Tars.
Again, I don't think we fully appreciate the sheer amount of data that this machine is processing in real time. Is autonomously, is that how you say it? Well, anyway, this is an AI agent that is processing an ungodly amount of data via sensors and making what if this is not deterministic, or at least, from obviously perfection maybe it's not achievable, but as close to perfection as possible in real time. This is not, let's schedule this, let's run simulations, and then 6 months later we'll know if they're all right. This is like, this needs to happen right now. Like, that's just, think about the amount of just science just that needs to go into that, like software, hardware, and everything else to be able to build such a machine. Yeah.
Come on, Tars.
I just had a funny thought. Do you think Thor's OS uses a borrow checker? Shit. Do you think Thor's operating system is written in Rust? Anyway. By the way, that was just me being a little bit of a troll, but also really hinting at the fact that however good we think we have it right now, there's still so much more that has yet to come if we allow ourselves to get there. And so you just wonder, like 10 or 20 years from now, are we gonna look back at Rust and be like, oh yeah, that was a thing that we did, and you know, are we gonna have something that is much more, that is much better? Except, you know, how do you define better? What does better actually mean, right? Anyway, it's just that you see things like this. Again, I'm fully cognizant of the fact that this is science fiction, but again, we can still, extrapolate or whatever. We're just, the thing that this machine is capable of doing, it's so removed from concerns like a borrow checker or whether to use what kind of allocator to use or whatever. And yet, they seem so removed, and yet there are trillions of decisions that had to be made over however long years to get to a point where you were able to build such a machine. And I guess the question is, at what point do we solve these fundamental primitive issues where we are now, like, there's like, are you able to build a machine like this while you still are worried about how a particular programming language is used to build something, or which kind of allocator is being used? I'm not saying that those problems do not need to be solved. If anything, I'm saying they need to be solved to the point where it's an afterthought. Like, it's just part of the fabric of how you build software, and you do software and hardware co-design, right? Because I feel like it's one of those things where it's like, I guess what I'm trying to say is, it's like trying to solve trying to do some sort of long-standing mathematical proof problem. Like, I don't know, it's like trying to, what is an example of a proof that we have yet to conquer, right? And it's like trying to do that while at the same time, it's like somebody trying to do that while at the same time trying to learn linear algebra. I don't know if that's a good example, but I guess what I'm trying to say is, for you to be able to crack one of those long-standing mathematical proofs, that, like, there is a grounding of there are fundamentals that, it's fair to just assume that you've solved them, or you're aware of them. It's part of, it's like the basics, you know what I mean? So the question is, like, how do we get to the point where we're able to build an AI machine like TORS? And I think in order for us to be in a position to do that, we need to evolve. We need to have evolved software and hardware to the point where concerns like a borrow checker, or the borrow checker being such a selling point of programming language, it's like becomes laughable. It's like, oh, it's like I don't know, some alien coming to Earth, and they're like, wait, you guys have not cracked speed of light yet? Okay, then you guys have nothing to offer us. like, like you guys are so primitive. Because it's like, oh, you haven't cracked light travel yet, then it's not. We can't even like talk. Like, there's not even. There's nothing to talk about. Like, we're not even on the same conceptual plane of existence. Whatever. Anyway.
Retro thrusters. Main engines on. Pushing out of orbit. Come on.
And if you pip this, he's basically prompt engineering. Cooper is basically prompt engineering here, or his vibe pilot. He's not vibe coding, he's vibe piloting, right? Because a lot of this he's just telling Toss to do it because he knows that's what needs to be done, but he's not the actual one pushing the buttons and doing all the machinations in the background. He's just telling it to do what needs to be done. And if at any point, the assumption here is that if at any point TOS analyzes the commands that are coming in and there's a problem in time and space of the coherence or the reasoning of those commands, it's going to flag it. Otherwise, it just, figures out how to best achieve it. It's like making a query to a Postgres database. You just write the SQL query. You're not the one figuring out which which exact query plan to use with, whatever query optimizations need to be applied specifically for this query. You can have some configurations or whatever that kind of guide the algorithm, but really, as you're making the request in real time, you're not controlling the optimizations. The database takes over and does it. It just needs to make sure that when it passes the SQL query string, that it makes sense, right? But once it's past that stage and everything checks out, like it's done the parsing, the interpreter has run, then you have the query plan, then you have the optimization, and then it needs to execute it. Anyway, so yeah, Cooper is prompt engineering. It's prompting TOS. It's vibe piloting.
Baby. Killing main engines. Okay, we're out of orbit.
Gosh, that is... Anyway, it has to be top. I don't know, maybe not 10. At least to me, personally, it's definitely top 10 science fiction scenes. How can it not be? Yeah. All right. How did we end up here? Oh gosh, I don't even remember. What made me come and watch this video? Oh boy, where's my cursor? I don't know why my computer. And this is a new Mac Mini. I think maybe I've left it on for too long and I have way too many things running. I'm gonna have to power cycle it or something. How did I end up here? Rabbit holes. All the time, everywhere. I think I was reading this. Open computing language. Never heard of it before. OpenCL. High level synthesis framework. For channels. Recon OS. I've heard of System C before. Are they listing these? Are they listing this in order of creation? I've seen AADL before. separate groups of programming processes. Virtual processes, virtual process. Is a different person to format the computational expressing to FPGAs as with Force Day, it offers a material approach. So a single deterministic MOC. System C is a system model language based on C++. It supports modeling both hardware and software and the interaction of multiple software. This is also based on a discrete event model. However, System C is mainly targeted hardware software co-simulation, not actual implementation. Blue Spec co-design language. It's a language based on a recorded atomic actions model, which can be compiled to both hardware and software. A BCL program consists of explicitly declared state variable and a set of coded atomic actions on these state variables. Compilation of such programs into an efficient finance device using the Blue Spec compiler. BCL introduces the ability to generate efficient C++ model, implementing the computation specified. Moreover, a program can be arbitrarily partitioned between hardware and software. A key difference between BCL and reactor is that guarded atomic action non-deterministic. Atomic actions enable simultaneously can be applied in any order. And this part here is handled by Lingua Franca. I think based on how they handle the whole super advanced time, but also, the order, the explicit order in which reactions are executed. Obviously, there's the stuff that we also just read with modal reactors. This is argued to be an advantage because it gives the compiler more freedom. Additionally, Lingua Franca only introduces a new syntax for coordination. The actual commonly expressed in language already familiar to the user. Yeah, this is actually a big selling point, at least at first. I don't know if in the long run, in the long run, if this thing blows up the way that, I don't know, Rust has blown up, which I think it can, right? And I have a feeling that it will do so when a big enough company uses it for simulation testing. I just had a crazy idea. Maybe I should try to rewrite some of the simulator code that is in the Limbo, the SQLite rewrite in Rust. I think I've seen them. They have some code relating to simulation. It will be, oh no, I just dropped it. Oh boy, I don't know why I'm trying to do this right now. as I'm streaming. Oh shoot. Sorry, everyone. For some reason, I've decided to be obsessed with my glasses, fixing something on my glasses, my second pair of glasses, right now on stream, for no real good reason. Yeah. Anyway, what was I saying? Yeah, something about how lingua franca, the fact that it's not a completely new language, it's actually just a coordination around existing languages. It's a big selling point. But I'm also saying that, well, that's great, but maybe at some point it may want to be its own language just because it doesn't have to carry a lot of the uh, gosh, what am I trying to say? A lot of the rust of its target languages. Right now, I think it's TypeScript, Python, C, C++, and Rust. I think that's actually a pretty good selection of programming languages to focus on. C and C++, obviously, because they definitely are trying to penetrate the embedded world, which, to the best of my knowledge, is definitely dominated by C and C++. Rust is starting to make some progress in that domain, but it's still it's very much still a distant competitor at this point. Obviously Python, because Python is everywhere. Everybody's doing Python. And TypeScript, because TypeScript, it's an easy buy-in to expose a lot of people. So overall, that's actually a very good selection of another crazy idea. Just what if you could build a deterministic hypervisor with Lingua Franca, or whatever this reactor chooser framework is, as like the harness around everything. I think there's something there. I should definitely send an email to Antithesis and tell them if they want to hire me to build that. It's deterministic DST. Yeah. Autonomous software testing. They build their own deterministic hypervisor. Insane. Anyway. Actually, yeah, I never heard of this before. Oh, nope. Gosh, I was supposed to do some ontology reading today again, but I don't know if I'll make it. What is the license on this? Is it, there's no license? Can anybody just use it? BSD3, yeah. Okay, that's good. So when they say it allows you to model, what does it say? Allow you to define hardware components. Does that mean that you can build models of certain GPU devices and then based on that run simulations? Let's say you wanted to know, you wanted to build a simulator to optimize your GPU provisioning in the cloud with respect to, you know, both service level agreements and costs. But I mean that you will have a way to basically model the GPU devices and then based on that run simulations, which then allow you to build the algorithm for the for the, I guess it will be a scheduler, the output of it. Documentation, user guide. Oh, it's a whole PDF, huh? Let's see. Blue spec, 76 pages. Doesn't seem too bad. Oh, but it's... Oh, okay, revision 2022. That can either be a good thing or a bad thing. A good thing would mean, you know, it's very stable. A bad thing would be, well, nobody really cares about it at this point. Or people have moved on to something else. The same way that Google has moved on from gvisor, the hypervisor, in their own infrastructure. At least for Cloud Run. I don't know if they ever used gvisor for anything else internally besides the infrastructure for Cloud Run. But the word is that they've moved on from gvisor already and they're already using something else. I think they're using a micro VM type thing. And yet, I don't know, I just remember reading something, I think it was on Hacker News, where people were basically making the case for gvisor and somebody responding and basically saying, it's funny, this article is basically interesting or funny because, you know, actually Google has already moved on from gvisor. Anyway, components of a BSV design. I just kind of want to see the design of it all. Is there... Okay, module and module. I was just looking for like a code block or something that was not necessarily on a hello world, but anyway. 2011. Has there been anything recent? Shoot, time is flying. Keep going on side quests. The range. Side quests. Let's come back. Reactor chisel. We might end up reading this. But then again, I say that about a whole lot of papers. Wait, can I just remove that? Okay. What the hell? Whiteboard? I didn't ask for a whiteboard. What is happening? What the hell was that? That was weird. I didn't activate any whiteboard stuff. Ooh. This paper has... Wow. Ay. Terrorist freedom out of mode. Side quests. Side quest. if one of the data structures that apply this to is a big tree. What is HP again? What are they calling HP? Is that just high performance? Let's at least read one or two pages because we need to make some progress on this. Okay. Models in the ontology. Organizations are looking to leverage artificial intelligence, AI, machine learning, ML, to accelerate and improve decision making. But the reality of operationalizing AI ML is complex, and the typical return on investment rarely lives up to expectations. Foundry provides the key capabilities necessary to bridge this gap. A trustworthy data foundation, tools for evaluating and comparing models against organizational objectives. Okay, let me reset. My mind was going in multiple directions. For a moment there, I was reading this, but also thinking about something related to what I was reading just now. Okay, reset. Okay, models in the ontology. Organizations are looking to leverage AI and machine learning to accelerate and improve decision making. True. But the reality of operationalization, okay, no, that's not the word. But the reality of operationalizing AI, ML is complex, and the typical return on investment rarely lives up to the expectations. True. Foundry provides the key capabilities necessary to bridge this gap. A trustworthy data foundation, tools for evaluating and comparing models against organizational objectives, and functionality for deploying models into user-facing operational workflows. This page focuses on the last step, deploying and evaluating model in production. End-to-end workflow. At a high level, these are the end-to-end steps required to operationalize AI ML in Foundry for live inference with the ontology. Create a model. Okay. Configure a direct model deployment. Okay. Publish a simple wrapper function for your model and optionally call it from another function to orchestrate complex logic around your model. Use the function for live inference in Workshop, Vertex, and other user-facing applications. What is Vertex? Okay, it's the visualization tool. Visualize and quantify. Holy shit. Couldn't you build and simulate an ontology using Lingua Franca? Oh shit. Oh shit. That's how we crack the code. using Lingua Franca, a reactor chisel. That research paper we just read, where they're trying to do hardware and software co-design, but then you retrofit that to build an ontology, and you basically your business as code set up where you basically operationalize the whole enterprise for automated reasoning. You basically build the whole enterprise as a simulation, as a state machine, and as a deterministic, or as deterministic as can be when you're dealing with actual real world physical time and space. But anyway, you build this digital twin of the enterprise, and you're able to just simulate. It's almost like being able to look into the future and then roll back. It reminds me of the TV show Devs. I think it was on FX. Devs. I guess this is technically a spoiler. Okay. I'm not gonna say anything. But yeah. Just now. Anyway. Alright. Let's refocus. Alright. Ontology objects can also be backed with datasets that leverage a model for batch inference. Benefits, just like mapping datasets to ontology concepts, provide benefits to workflow development and decision making. Mapping models to the ontology provides a number of benefits. Interpretability, because all modeling results are defined in terms of real world concepts, and users do not need to understand machine learning in order to use modeling results. Instead, users simply interact with simple concepts such as forecast, estimate, or classification. Economies of scale, instead of each modeling project being a bespoke effort created in service of a specific use case, modeling efforts can build on each other over time. For example, a forecast produced by for one use case can immediately be used for subsequent use cases as well, reducing the duplicated effort and providing end user value more quickly over time. Connectivity at scale. By incorporating ML models, the ontology becomes a single source of truth for the organization, not just in terms of data, but also in terms of logic. Models encode the organization's expectation for how things may change in the future, i.e., being able to simulate things. In this way, the ontology becomes a digital twin of the entire enterprise. They not just say this, which unlocks the ability to simulate changes across the organization in ways that will never be possible in a wide array of disparate modeling efforts. That's right. Okay, core concepts. This page describes major concepts. Okay, ontology. An ontology is a categorization of the world. In Foundry, the ontology is the digital twin of an organization, a rich semantic layer that sits on top of the digital assets, datasets, and models integrated into Foundry. Okay, so data is everything, right? Especially now that we have AI, I think people are waking up to the fact that whatever, like part of your moat, if you have any, is your data. Um, so the ontology is a way to make sense of that data in a way that allows people at different levels of the enterprise to be, effective decision makers, being able to assess risks, and make optimal decisions with respect of time and space. Yeah. So yeah, data sets. So you have all your data sets across different sources. Sounds like what Foundry allows you to do is to put in all that data, but not just to sit in some data lake somewhere, and then you have to ad hocly. Is that a word? Ad hocly. I don't know if that's a thing. In an ad hoc way, access that data for specific use cases and all that. So you could do that, or you could build on an ontology on top of it, and then leverage the ontology to achieve particular use cases, or even simulate use cases before even having real implementation of them. The Foundry ontology creates a complete picture of an organization's world by mapping data sets and models to object types, properties, link types, and action types. An object type defines an entity or event in an organization. Okay, entity or event. A property defines the object types, characteristics. Okay. So it sounds like just thinking in terms of simulation and game engines. Object types or entities, property and link types or components, or also specifically in terms of ECS game engine. ECS game engine, and action type will be some form of, the system, like the system of actions that runs on every frame. Okay. The concepts that comprise the ontology hyperbolas in the structure of a data set. You can think of each object type as analogous to a data set. Excuse me. An object is an instance of an object type. Just as a row is one entry in a data set. Okay. But I feel like a data set is more than just a table, though. A data set can usually also, it can actually be a folder of different kinds of data, like a folder of JSON, CSV, and images and videos. You can wrap all that up into a single data set and provide some interface to access all of those things. Yeah, basically, I guess what I'm trying to say is a data set need not be just a single data table. It can represent just a bag of heterogeneous data buffers. You know, it's just ones and zeros, just different kinds of ones and zeros that do not necessarily fit all in a single table. Anyway, the columns in a dataset are analogous to properties of an object as they provide additional information for a given row. The value in a dataset field, like a cell in a spreadsheet, is akin to the property value of an object. And just as datasets can be joined together in various ways, objects have links between them based on property values. Okay, this is helpful. The diagram below demonstrates how these concepts can come together to create an ontology. The content below continues to define the different components of the ontology in more depth. So the object type here is an airport object, JFK properties, opening dates, operating capacity, lat long. Alright, yeah, okay, properties are columns. Just following this mapping here. So you have the data set. JFK will be a row in the table. So you could say that this is the airport table. Each row is obviously an instance of an airport. The properties here will be the columns of the table. These are links. So you need to actually label the links. Departed from, arrived to, this is a plane or a flight. Oh, interesting. Yeah, this is a flight. Although, oh, okay. So here you have object type aircraft. So there's the actual physical aircraft, and then there is the flight. Delayed by, operated by. I mean, if you were to map this into a Lingua Franca program, would I guess you could represent each data set as a reactor. And then you can have sub-reactors for properties. I don't know. I'll have to think about it. Anyway, all of this makes sense. A simple ontology of 5 object types displays some of the properties and relationship within an airline industry datasets. Object type. An object type is the schema definition of a real-world entity or event. An object refers to a single instance of an object type. An object corresponds to a single world entity or event. An object set refers to a collection of multiple object instances. That is, an object set represents a group of real-world entities or object types. An object set refers to a collection of multiple, so some sort of, just a filter from a table, for example, would be an object set. Like, again, doing the mapping to the usual relational modeling or tables that people are used to. There is an object set represents a group of real-world entities or events. Property. A property of an object type is the schema definition of a real-world entity or event, or a characteristic. I think I missed that part. A property value refers to the value of a property of an object or a single instance of the real world. Okay. So we have property value, object type, and object. Shared property. A shared property is a property that can be used on multiple object types in your ontology. Just reading this, I think it's obvious that your RAG, retrieval augmented generation, will be can be drastically improved if it's built with an ontology as the platform for it, or at least as the ground truth for it. Basically, the ETL that you do to index stuff is mapped onto whatever ontology you have, and then you can fine-tune a model on the ontology rather than on the data set that is mapped to the ontology. To get better results. Anyway, shared properties allow for consistent data modeling across object types and centralized management of property metadata. Excuse me. All right, shared properties. My mind just was wondering about, how do you handle backwards compatibility when you have to make changes to these shared properties? Link type. A link type is the schema definition of a relationship between two object types. A link refers to a single instance of that relationship between two objects. Action type. An action type is the schema definition of a set of changes or edits to objects, property values, and links. that a user can take at once. Are these changes meant to be? Oh well, okay. It says a set of changes. So really, an action type is really a transaction. If you're thinking about it from a database perspective, it's like a bunch of statements that are meant to update a bunch of records or make changes to the database, all being run as a single atomic operation. It also includes the side effect behaviors that occur with action submission. Once an action type is configured in the ontology, end users can make changes to objects by applying actions. Excuse me. Roles are the central permissioning model of the ontology, or in the ontology. Similar to roles in a Foundry file system, ontology roles grant access to ontological resources. Roles can be granted on the ontology level or the individual resource level. Learn about ontology roles and how they are used for object types, link types, and action types. Functions. A function is a piece of code-based. Logic that takes in input parameters and returns an output. Functions are natively integrated. Oh, no, nothing just crossed my mind. So maybe you don't use React or Lingua Franca. Well, you could still do that. But if you were really if you were trying to follow standards or whatever, and take a model-based engineering approach, you could define your ontology using SysML v2. Okay, we're almost there. Interfaces. An interface is an ontology type that describes the shape of an object type and its capabilities. This is not very clear to me. An interface is an ontology type that describes the shape of an object type and its capabilities. It's the first mention of the word capabilities. Is it more like, here's a table and here are all the allowed queries for that table? And then you expose that as an interface. It's almost like an ORM model, where you define a schema and then you can then use that to make some database requests. Like you will say, let's say you define the user ORM model, then later in your application you can do user that I don't know what something. User that filter by something. I feel like that's what this is. Anyway, object views. Object views are a central hub for all information and workflows related to a particular object. Object or object type. This includes key information about an object, any linked objects, and okay, no, it is an instance of an object type. This includes key information about an object, any linked objects, and related metrics, as well as analysis, dashboards, and applications related to the object. All right. I think we'll stop here today. How long was this? Oof, 2 hours and 45 minutes. All right. I'm gonna call it for tonight. Thank you for joining, watching, or whatever. Well, joining or watching later on. Yeah. I'll see you guys around. Have a good night.